For decades, silicon followed a simple and brutal rule. When a chip fails, you throw it away. That rule made sense when chips were cheap, simple, and easy to replace. It doesn't make sense anymore. Today, a single AI accelerator can cost tens of thousands of dollars. Automotive chips are expected to operate reliably for more than a decade. A single defect can shut down a data center rack, factory line, or entire vehicle platform. So the semiconductor industry is changing its mindset. Chips are no longer designed only to avoid failure. They're increasingly designed to survive it. Hello and welcome back to Chips Weekly by Diana. I'm Diana, and today we are diving into a quiet but fundamental shift in chips design. For most of the semiconductor history, chips were disposable. When something went wrong, replacement was cheaper than repair. Modern silicon is too complex, too expensive, and too critical to treat it that way. Today, chips are being designed with fault tolerance, redundancy, and recoverability built directly into the silicon. This is not about science fiction. It's already happening inside AI accelerators, automotive processors, and advanced CPUs. Let's break down how and why this change is happening. At all the technology nodes, chips were relatively forgiving. Defect rates were low, dies were smaller, and yields were high enough that the failures could be absorbed economically. That logic breaks down in advanced nodes. At 5 nanometers and below, every square millimeter of silicon becomes dramatically more expensive. Defects are harder to eliminate. Losing a single large die can mean losing tens of thousands of dollars in value. This is one of the reasons the industry moved away from monolithic chip designs. A single defect in monolithic chip can kill the entire processor. That risk is no longer acceptable when chips power AI clusters, vehicles, and industrial systems. The economics forced a redesign of architecture itself. The first major shift came with chiplets. Instead of building one massive piece of silicon, companies like AMD began splitting processors into smaller functional blocks. Compute, memory controllers, and input-output could be manufactured separately and then combined into a single system. Intel followed with advanced packaging technologies. Apple applied similar principles in M-series processors, tightly integrating multiple dies into one package. Chiplets don't just improve yield, they create isolation. If one part fails and degrades, the rest of the system can remain functional. This is a structural foundation that makes repairable and resilient silicon possible. Repairability in modern chips is rarely physical, it's architectural. Memory manufacturers like Samsung, Micron, or SK Hynix have used redundancy for decades. Every DRAM chip includes spare rows and columns that replace defective ones automatically. That same philosophy is now expanding into the logic and interconnects. Modern processors include spare compute units, redundant routing paths, and error-correcting mechanisms that allow chips to map around the damaged areas. Instead of failing, the chip adapts. That's why large processors today often shift with more hardware than strictly necessary. Some of it exists purely as insurance. None of this works without advanced packaging. Technologies from TSMC, Intel, and Samsung allow multiple dies to behave as one system, while remaining physically independent. Compute, memory, and input-output can be combined without being fused into a single point of failure. This is critical for AI hardware. NVIDIA's modern accelerators rely on stacked high-bandwidth memory from SK Hynix and Samsung, connected through the interposers. Packaging the region of fragile, these systems wouldn't scale. Packaging is no longer just a protection, it's a repair enabler. Modern chips don't survive on hardware alone. Enterprise processors from Intel and AMD rely heavily on software-based monitoring, error correction, and dynamic control, voltage, frequency, and workload distribution. constantly adjusted to avoid stressed or degraded regions of silicon. In automotive and industrial systems, some companies design chips to meet strict safety standards. Hardware isolation, fail-safe modes, and redundancy are mandatory, not optional. In these systems, software doesn't just run on the chip, it actively protects it. Repairable silicon is also becoming an economic and environmental necessity. Advanced chips require enormous amount of energy, water, and rare materials to manufacture. Extending their usable life reduces waste and lowers the effective cost per unit of compute. Governments funding semiconductor manufacturing increasingly care about yield, durability, and life cycle efficiency, not just the raw performance. A chip that delivers slightly less peak performance but lasts twice as long is often more valuable than one that fails early. This transition is already visible in the strategies of the leading companies. AMD designed its processors assuming partial failures will occur. Intel is rebuilding its roadmap around the modular, recoverable architectures. NVIDIA depends on fault-tolerant memory and packaging to scale AI systems. Apple co-designed silicon, software, and reliability as one of the products. Automotive suppliers have treated repairability as a baseline requirement for years. Repairable silicon is no longer a niche feature, it's becoming a competitive advantage. The future of the chip is not just the fastest silicon, it's silicon that can fail gracefully. As chips become more expensive, more essential, resilience will matter as much as the raw performance. The winners won't just be the companies that build the fastest processors, but the ones that build silicon that survives the real world. So let me ask you, should repairable chip design become standard even in consumer electronics? Or will this remain limited to AI, automotive, and critical infrastructure? Share your thoughts in the comments. And if you enjoyed the special edition of Chips Weekly by Diana, like, subscribe, and share it with your network. And as always, stay curious, stay sharp, and stay chip aware.